150 million degrees
150
Celsius.
million Celsius,
Wow.
degrees Celsius. When a fusion power plant actually operates, they are the hottest places in the solar system.
How do you get these two heavy hydrogens to stick together?
Fuse those two together and you get a 17.5 mega electron volt reaction.
So there's a safety question. What are the other reasons why fusion hypothetically could be more beneficial than fission?
In it, because once we've got it, it's such a clean, source of energy that the whole world will hopefully want to do it, and it's limitless.
Hello everybody and welcome back to another episode of Modo the podcast. In this episode, Quentin is joined by Dr Mark Wenman, Reader in Nuclear Materials at Imperial College London and Director for the Centre of Doctoral Training in Energy Futures. If you're enjoying the podcast, please consider hitting like and subscribe. It really means the world to us. Let's jump in.
Mark, thanks for coming on the podcast. Should I call you a professor?
Well, strictly speaking, I'm a reader.
Reader?
Which is a old English kind of term for someone. Well, it comes out of theology actually, but it's the sort of used to be an interchangeable term for professor, but it's sort of become one sort of below professor in that. But Alan Turing was a reader, so
Okay.
I'm in good company.
I didn't mean to rub it in then. If it was 100 years ago, maybe. Mark, thank you very much for joining us on the podcast. Today, we've got you on because you're an expert in all things nuclear. We're going to talk about one specific part of nuclear. I know we could talk about all aspects of metallurgy and fission and fusion and building stuff and decommissioning stuff. But today we're here to talk about fusion primarily and how that works and when it's all going to be finished. So
The big question.
The big question. Mark, before we get started, can I just ask you to explain who you are and how you ended up coming on this podcast or in energy?
Okay. So I'm a reader in nuclear materials at Imperial College London, but I'm also the director of the Centre for Doctoral Training in Nuclear Energy Futures, which sort of trains a lot of the PhD students in the UK who are interested in nuclear energy, whether that's fission or fusion energy.
Awesome. And how long have you been doing nuclear stuff?
I've been in the nuclear industry since I was an undergraduate, which I have to say now is more than 25 years ago, sadly. And that's mostly been nuclear fission. I have to say I've worked in nuclear fission for that sort of period of time and probably only started in nuclear fusion in the last sort of 5 years. It's a really growing area now in the UK.
And in the last 25 years, how have things changed in the world of nuclear? Because we haven't actually built any more nuclear power stations in the last 25 years, have we?
So, nuclear used to provide a much bigger fraction of our electricity. It probably peaked in the 90s. And then since then, the last reactor we built was Sizewell B in 1995. And we haven't built any since then. And slowly our fleet of advanced gas-cooled reactors, which EDF Energy own, are being decommissioned. That's sort of happening over the next sort of 5-year period. Of course, we are building one big new reactor, which is Hinkley Point C, which is a behemoth of a reactor. It produces 3.2 gigawatts of electricity. So that's on the books, and that's coming close to completion. I think it's 2027 that will be connected to the grid. And then we've got Sizewell C, which is a sort of sister plant to that over in Suffolk, which is in the planning, but hopefully a bit more than the planning stage now. So they hope to sort of start building that soon. But we're at an exciting period because Rolls-Royce, who many people wouldn't know actually build nuclear reactors, they are actually, they've built submarine reactors for the UK since the 1950s. And they are planning to build a series of 16 small modular reactors, which again would, if they built all 16, would add another 7.5 gigawatts of nuclear electricity to the grid.
Okay, so just under 500 megawatts each. 450 megawatts each.
470 something megawatts is what they quote as the electrical output.
So that's considered small. So half of CCGT is a small modular reactor. So they're still quite big.
They are big, yeah. That's just where the economic works really for nuclear reactors. So, I mean, there is actually a definition which says small is 300 megawatts, but it's an arbitrary definition. You know, it doesn't mean anything. And when they did the calculations, it just turns out there's a sweet spot around the sort of 500 megawatts for connecting it to the grid and getting the economics right.
And so we've got operational big multi-gigawatt plants and, of course, Hinkley Point C and others coming, which is nice and absolutely necessary. And then we've got small modular reactors, which is a newish technology around the 500 megawatt mark. And all of this stuff we're talking about here is nuclear fission, right?
Yes.
Which is Can you just explain what fission is? And then we're going to talk about fusion and what's happening there.
Okay, so let's start with where nuclear energy actually comes from. And that's, everyone will have known the most famous equation, E equals mc squared, right? In fact, I just saw it on the back of a backpack as I was getting off the train at New Street. And that basically tells us that energy is equal to mass, so it's their equivalent, but mass times this speed of light squared, which is a huge number. So a tiny bit of mass turns into a lot of energy. And so you can either split certain atoms. So if you have very, very big heavy atoms like uranium, then you can split those, and that's called nuclear fission, and that will release energy. Or if you have very light atoms, you can fuse those together, and by fusing them together, you also get energy out. And you get lots of energy out. So the energy density is by far the sort of biggest energy density of basically any energy producer that you could think of, really.
And this is why you can, from such a small amount of substance, create so much energy for so long.
Yeah, I mean, it's in terms of chemical energy. If you think about fossil fuels, it's sort of hundreds of millions of times the energy density of a fossil fuel.
Take that, fossil fuels. Very good. And so the world of fission, that's quite an old technology, isn't it? We've been doing that for almost 100 years, is that right?
Nuclear fission was discovered in the 1930s. Lisa Meitner is the person who's credited with first explaining the process of nuclear fission. And that came at the time just before the Second World War. And of course, that actually drove a lot of what happened because people were worried about Nazi Germany getting hold of the technology, and they certainly did try to get hold of that technology. People may have heard the famous stories about the Norwegian heavy water tanks that they went and blew up in the Second World War, and that was Germany's effort to get a nuclear weapon. But at the same time, of course, that was driven by the US, and they, of course, did achieve that. But the spin-off from that was in the 1950s in the Atoms for Peace conference in 1953. And at that, the US said, we will release this sort of technology to the world and share it with the world, but for peaceful means. And so the energy part sort of started to separate from the more nefarious parts in the 1950s. And it's been separate since.
And
really.
Now both camps are very separate, right?
Yeah.
You don't have the nuclear weapons guys hanging out with the nuclear power guys.
I mean, no. Yeah. So nuclear energy is a completely separate entity in civil nuclear.
And before we get to fusion, what is this word fission? What's all that about? And how does that generate power?
So basically, it comes from this premise of E equals mc squared. And when you split the heavy atoms, you actually release some of the nuclear energy inside the nucleus by converting some of the mass into energy. And as I said, when you multiply it by that C squared term, you get a huge amount of energy out.
And what's a heavy atom?
So a heavy atom just means something at the far end of the periodic table. So the heaviest things that we can actually get naturally is uranium, which has a mass typically of 238. And that means it's got a lot of neutrons, and it's kind of becoming unstable at that point, and so it's not that difficult to cause it to split. If you hit it with a neutron and it absorbs the right neutron, although I have to say it's uranium-235 that we typically...
Not 237.
No. So there is very specific isotopes, but uranium-235 is the one that we can split. And we can split it very easily.
And this is quite far down the periodic table, isn't it? So that's why it's heavy.
Yeah.
I don't even think the song gets that far, does it?
I'm not sure, to be honest.
10th verse or something.
Yeah.
And saying, where does this stuff come from?
Well, uranium, as I said, is easy for us to get hold of because it's in the Earth's crust and we just mine it. And there's various mines around the world. There's big ones in Australia, for example. There's sources in parts of Africa and Canada and Kazakhstan and places like that. So, there's lots of sources of uranium. It's not a particularly rare resource.
Okay, so this fission technology is getting a heavy mass or a heavy atom, and which is quite unstable or tending to instability. I don't know, I'm losing myself in the words here. And then you split it and create a load of energy with this E equals mc squared equation. And from that, you create some heat, and then the heat creates, I assume it's then steam and then...
Yeah, it's pretty much like a coal-fired plant at that point. It just literally heats up some water. Usually there's different designs, but the most popular design is something called a pressurized water reactor, and that pressurized water reactor has two loops. So it's a bit like the primary loop is a bit like the heat element in your kettle. It's the hot bit, and then around that you put some secondary water, which, like in the kettle, boils, and that goes off to produce steam to your turbines, and that's it really.
Simple.
Yeah.
So you just have a different heat source, and the rest of it is like a coal station.
Yeah.
And that is fission. So what's fusion then?
So as I said, fusion's where you can actually fuse together very light elements. And typically, the sun does it. That's where most of the energy in the world comes from, of course, is from the sun. And they worked that out not long after Einstein's equation, that this is what the sun was doing. And it fuses together hydrogen atoms, the lightest of all. Now, actually, it's more difficult to fuse pure sort of H1, if you like, light hydrogen together than to fuse heavy hydrogen. So on Earth, to make life easier for ourselves, because we don't have lots of gravity, so the sun burns at 15 million degrees, but it has a huge amount of gravity to pressurize the atoms together as well. We don't have that on Earth. We don't have the gravity aspect. So we have to get to 150 million Celsius typically, or between 100 and 150 million Celsius.
150 million degrees
150
Celsius.
million Celsius, yeah.
Wow.
Degrees Celsius. Now, when a fusion power plant actually operates, they are the hottest places in the solar system.
Right, okay, let's just take this back a second. So fission is where you take a heavy atom and split it apart. And fusion sounds a bit like the opposite. You take a really light atom like hydrogen, and then you squeeze them together?
You squeeze them together. And if you think about how difficult that is, if you think about what the nucleus of an atom is, and that's where nuclear energy comes from, it's all in the nucleus. The nucleus is a ball of positively charged protons. And if you think to yourself, well, how does that stick together? Because they should be repelling each other, because they have this positive repulsion, and they should be trying to throw each apart. But when you get to very, very tiny distances, and I mean 10 to the minus 15 meters, then a new force comes into operation called the strong nuclear force and binds those protons together. So if you can then
very convenient, mathematicians, that at a certain size where you can't see it, it all sort of works.
If you can get two protons to get really close together, but you've got to overcome that positive charge to do it, and that takes a lot of pressure or a lot of temperature or a lot of both, frankly, then that strong nuclear force will take over, bind them together, and a little bit of mass will be released as energy, and you get a lot of energy out.
And even that tiny bit of mass, so just by having two light atoms and pushing them so close together they don't repel, that they stick together, that releases some energy, and that is enough, is it, for a power station?
So, as I said, if you compare the sort of energy release from fusing deuterium and tritium, which are two heavy isotopes of hydrogen. So deuterium is a proton plus one neutron, so it has mass 2, and tritium, you might guess, is mass 3. You fuse those two together and you get a 17.5 mega electron volt reaction. And as I said, if you compare that to the few electron volts that you get out of a carbon sort of oxygen reaction chemically, it's a huge amount of energy. So you don't need very much volume of that material to get huge amounts of energy out.
Okay, so you get these heavy hydrogens and you put them together and they bond and they stick to each other, and that releases some energy. And then how are we going to turn that into power?
Well, then the process becomes very similar to what you do with nuclear fission, to be honest. It's a bit more challenging because sometimes we haven't talked about how you're going to get those two to to push together, and perhaps we could talk a bit more about that in a minute. But you've got other sort of bits, often magnets around them and things that get in the way, which you don't have in a nuclear fission power plant. But still, you're ultimately generating heat. You're going to put that heat probably into some kind of coolant to take it away. It could be a liquid metal, it could be water, and then you again put that through another loop and generate steam at the end of the day.
So again, you're heating another thing, and that thing creates the electricity through a turbine or something else.
There are a few other technologies which don't do that, but yeah.
Well, now let's talk about what you mentioned there, how you do it, and this is where we're going to get well into the James Bond's evil guy's lair with words like magnets and lasers and all sorts.
Yeah.
So how do you get these two heavy hydrogens to stick together?
So the first thing you've got to do is you've got to create what we call a plasma. And that's basically a soup of sort of particles. So you have to get it hot enough that you start to strip the electrons away from the nuclei. So it just becomes this sort of gloop, or sort of a gaseous gloop of nuclei and electrons. And that means those are already at very high energies.
Plasma. Is this a physical thing you can see? Is it how big is a bit of plasma?
It depends how big you make your reactor. But let's say you were talking about JET, the reactor in Oxfordshire. It's a sizable. I mean, it's not huge, but it's sizable. It's meters high, and the plasma would contain inside this donut-shaped vacuum vessel. And of course, it is a vacuum vessel, has to be held at a vacuum because you don't want anything getting into your plasma. And it is a sort of gaseous substance. So if you didn't contain it in some way, it would just sort of, start to go everywhere. So that plasma's then got to get up to 150 million Celsius. So you've got
this thing in like a donut, like a horizontal donut, right? That's I'm thinking about Saturn's rings kind of shape. Is that what plasma looks like?
Well, I mean, it's hard to visualize, and I'm not a plasma physicist, I should say that. I'm a materials engineer, but it's held in place by two sort of sets of magnets. So you have a magnet which goes around the coil magnet, and then you have another set of magnets which make it rotate around the ring. Okay, so poloidal and colloidal, poloidal, and I got my words all tongue-tied there. But yeah, so you have the ones that make it go around the circumference of the ring, and the ones that go around up and down. And that contains it and stops it hitting the walls of your vacuum vessel. So that vacuum vessel, of course...
So it's floating?
It's
floating on magnets,
completely
right?
contained. It's completely magnetically contained.
You said something that seemed obvious to you, but wasn't very obvious to me. You said, of course, you don't want anything getting in your plasma. What happens if you get something in your plasma?
Well, it's very hard to keep this plasma alive, so to speak. So to keep that reaction going of the deuterium and tritiums, right, we actually mustn't poison that reaction with other species. So if it touched the walls of your vessel and things like tungsten, which we often make the walls out of, got into it, they start to poison the reaction and stop it from happening.
Oh, okay, so you need it pure. Okay.
So you need to keep it pure. And equally, one of the products of the reaction is actually helium, which is like your exhaust product. It's like the CO2 from a kind of fossil fuel, but not as nasty, obviously. So you need to get the helium out as well through an exhaust. Yeah, they have an exhaust at the bottom called a diverter.
A fusion reactor's got an exhaust.
Yes, it does.
Brilliant. And let's get an idea about size here. Is this thing the size of this donut? Is it the size of, I don't know, a fingernail or a car or a house or an office block? I don't know what's going on there.
So if you took JET as an example to begin with, JET wasn't made big enough.
What's JET? The one in Oxford?
Yes. So the Joint European Torus.
Is that a Culham?
It's at Culham in Oxfordshire. It was built in the late 1970s, started operation in 1980s, and it's been our main research reactor for magnetic fusion for a long time.
That one's been in the news quite a bit, hasn't it?
Yeah, so it set various records over the time. So it set the record for the amount of fusion power back in the 1990s. It never quite got to this break-even point where it, the amount of energy that we put in to contain the plasma and get it to do what we want it to do was less than the amount of energy that we then got out of the fusion reactions. It got to about 2/3 of that. And that's the key thing. So when we go back to size, they didn't make it big enough to get there. They designed it to do that, but they didn't quite get the design right. And so it's probably, it's bigger than the room that we're sitting in. So it's bigger than a room. It's not as big as a house.
Okay. Somewhere between a room and a house.
But if we went to the next generation, which is ITER, the next experimental reactor, that's very much the size of a house.
Okay.
Yeah.
And these are bigger donuts. Just excuse my ignorance here, but it sounds like the reaction itself to create this plasma and push these big heavy hydrogens together and create some energy, that reaction sounds quite straightforward, but then making it all float around and keep it in the right place and not poison it and get the exhaust out, that all sounds like really complicated bits on top of what is already a fairly complicated nuclear reaction. And is it all those ancillary bits which are the pain in the backside?
Yes. Yeah, to be frank. I mean, it took a while for the plasma physicists, to be fair, to get to the point where they were happy that they could control the plasma and get the plasma they want. If you talk to the guys at Culham, they will tell you that that's a done deal. And ever since then, it's about how do we make the engineering work to do this. So there's lots of bits of nuclear fusion that we've never worked out yet because we haven't been able to, because we haven't had a reactor that runs for long enough to actually test some of these things. One of which is how do we actually generate the fuel? Because tritium, we can't get that very easily. It doesn't exist in nature. We can get deuterium out of seawater, loads of it, no problem. So endless fuel there. But the tritium we have to actually make in the reactor as part of the reaction.
No way.
So we've never worked out how to do that properly. There's lots of theories. So if you take some lithium and bombard it with neutrons, which we have lots of because we're in that sort of environment.
We've already stolen all the lithium for our batteries. Thank you very much.
Yeah, we don't need much of it though. That's the thing. We don't need much of it.
Okay.
We're really tiny amounts. But we do need to work out how we make the tritium that's going to sustain the reactions, because we don't have enough tritium in the world to do it currently.
Wow, I didn't know that. And this is awesome, right? How long? So you mentioned then that we haven't got a reaction to last long enough. So what do you mean by that?
So, I mean, and there was another record recently also set at the jet reactor where they were trying out things in preparation for when ITER turns on in 2025, fingers crossed. And what they were trying out was, does the engineering work? Now because they were built in the 1980s, essentially, early 80s, their magnetic system runs off copper wires. So it heats up, the resistance of copper wires heats up very, very quickly. And our magnet technology's come on a lot since then. But nonetheless,
and whatnot.
Yeah, so they ran that experiment for just 5 seconds. That was the world record. So they produced the most fusion energy, which was 59 megajoules, which is not a lot.
59 megajoules.
I've read it's 60 kettles worth of boiling water. I've not actually calculated it myself to check, but that's what I've read. So it's not a lot, but it was at a rate of 11 megawatts, which is sizable amount of energy coming out. It's 2 big wind turbines or something like that. And they ran it for 5 seconds, and they couldn't run it for any longer because they would have overheated the whole system.
Wow, that's sinking a lot of power then, isn't it? If you can only put it for 5 seconds and then the copper heats up.
Yeah.
So, wow.
And then if you go to ITER, it will have superconducting magnets, so they don't have that problem. And then the idea is they will run that for hundreds of seconds, maybe even hours. Maybe, we don't know what we will get out of ITER yet, but I think the target is to get to an hour of plasma running. And once you get to that point, we can start to do the experiments on things like the fuel cycle, the engineering, the materials, and all of those things that we still don't yet have a handle on for nuclear fusion.
This is incredible. I mean, we're still quite early, aren't we? We're still quite early in this game. So I'm going to do the really annoying question now, the Daily Mail question, which is, it's not going to be finished on time, and when are you going to finish it, and is this thing even going to be real? So when does this become commercially viable? When do you put pounds in or dollars in and get dollars out?
Yeah, well, if I did know the answer to your question, I would probably be investing, and I don't. But I'll give it my best technical guess. So I mean, we haven't touched on the fact that there's a lot of money now pouring into private fusion companies as well. So I've sort of highlighted the sort of big kind of European projects there, and the big world projects. ITER's a world project. But now there's lots of technologies which saying we can do this smaller, we can do it more compact, we can get it to market quicker. Some of those companies, I mean, I think the biggest boast is Helion. They say that they're going to... Helion, yeah. They say they're going to break even, so get to that magic break even energy in, energy out figure next year.
Wow.
Whether you believe that or not, and then they say they're going to put electricity on a grid in 2028.
Go Helion.
The skeptic in me says that, of course, all these companies are competing for investment, and they're getting hundreds of millions now in investment. If they're the one that says, oh, well, actually, we won't get ours on the grid till 2045, and someone else is saying we're going to get ours on the grid in 2030, who's the investor going to invest in? So they all kind of, I think they're all bringing their dates a little bit back, and that's the sort of reality. And perhaps you could argue that they're saying they're not completely unrealistic. They're just saying it's a bit like when you get a builder in and he says it's going to take 8 weeks to build your extension. Well, that's true if everything goes right and he doesn't find the electrics need rewiring and as you do when you start doing these things. And I think that's where we're at.
Well, unless he gets a bonus if he finishes on time, which I get some of these private companies do, right? If they manage to do this stuff, then there's a big incentive at the end for them.
The payback would be huge.
So what? Again, I'm going to ask some really basic questions here because hopefully you can answer them in a very simple way. Why even bother with fusion when we've got fission? And fission is pretty safe now. I know we had the Japanese accident and whatnot, but fission is pretty amazing and it just goes and goes and goes. So why bother with fusion? What's the benefit?
So there's a few benefits. One is that no matter how safe you make it, you're always going to have, I spend quite a lot of my time talking about things like Chernobyl and Fukushima, and you can't get away from that public perception. You're never going to get completely away from the public perception that there is a problem there. Nuclear fusion, of course, doesn't have that problem. So it doesn't have that image problem in that sense. The other one, of course...
But is it, on that, is it safer? Is there less chance of a runaway reaction, meltdown, all that?
Yeah. So the simple answer to that is yes. It is. You would need less protection in place for a nuclear fusion reaction. The worst thing that can happen is that you release some of the tritium, which is a radioactive material, but being hydrogen, it will just go into the atmosphere and disappear, and no one will ever see it again. Frankly. But we do look at tritium releases. That's one of the things we do need to look at. But it's not the same as the sort of release that you've got from Chernobyl.
The chain reaction that just keeps...
Yeah, well, that's the other thing, is that the chain reaction in fission, you need to continue to cool it beyond the point where you've shut down the reactor. Fusion, that's not the issue.
Yeah. Okay. So there's a safety question. What are the other reasons why fusion hypothetically could be more beneficial than fission?
So the other one is abundance of the fuel. I mean, we're never going to run out of deuterium, and provided,
tritium.
But we can make the tritium.
Okay.
So that's the thing. So if we can make the tritium and we can get that reaction working, then we have fuel for forever and ever. It's never going to run out, basically. And the final thing is, of course, a lot of the other reason that people generally don't like nuclear fission is the nuclear waste that it generates.
Yes.
And if you're talking about nuclear waste, you don't get the long-lived nuclear waste actinides that you get with nuclear fission. So you will get some intermediate level waste. Anyone that tells you that nuclear fusion comes with no nuclear waste is not true, but it only lasts for like 200 or 300 years. And frankly, you can put that in a building and look after it for 200 years. And
not a gazillion years or whatever it is that...
It's a different proposition to looking after the nuclear waste from fission.
Okay, so there's a couple of big benefits there. One of the difficult things for me is for us to get to net zero by 2050, or what we've committed in the Paris Accord, or we've got a pretty good idea. Some of the modelling could be questions. We've got a pretty good idea about how we prevent climate catastrophe if we do certain stuff with decarbonisation and equivalents. But we kind of need to get started on that now. We need to be building, financing, operating zero or low carbon infrastructure now to make sure we slow down that curve of carbon emissions now. And if we have to wait 30 or 40 years to get till fission's there, it's almost too late to solve the decarbonisation problem. That doesn't mean we shouldn't do it, though, because it might solve a different problem that we have then, which is we need a lot more energy for other things. I don't know. But how do you and the community think about that challenge?
So when you said fission, I think you meant fusion.
I meant fusion, sorry. We're going to have to keep on. Izzy, can we dub me in with fusions and fissions, please?
Okay. So with nuclear fusion, I think there's a lot of people out there that obviously have a vested interest in saying that it will contribute to net zero. But that would only be true if some of these startups genuinely live up to their promise and we can start to build reactors that you can connect to the grid in the 2030s.
Yeah.
My view is that is slightly over egging the pudding. And I think we'll have fusion probably in the 2050s, 2060s sort of time frame.
Yeah.
But as you say, that's not to say we shouldn't be doing it, because once we've got it, it's such a clean, source of energy that the whole world will hopefully want to do it. And it's limitless. So, we could decarbonize Africa, for example, if we went and built them a load of fusion reactors in the future. So it still has a place for me in that energy mix, but in the other half of the century.
Yeah, so it's not the thing that's going to save the planet right now. But that doesn't mean it's not an amazing technology and we shouldn't be spending time on it.
No, absolutely. Yeah.
So let's talk about how this is. So typical nuclear development. So I'm going to talk about fission or nuclear weapons here. That was like a global race between big superpowers to learn about that technology. But now with fusion, it's a bit different, isn't it? Can you talk a little bit about who's involved and what that looks like?
Well, so the fusion community, as I said, they've been largely up until recently, they've been big international projects. I mean, if you take ITER, that came out of a meeting between Reagan and Gorbachev in the 1980s. And it has...
ITER, the one they're building now?
Yeah.
They've decided to do it 40 years ago.
Yeah. And that's a slight problem in that if you were building ITER today, you wouldn't build it the way that they are building it. But that design got locked in so long ago, and it's such a complex process because they have so many international partners. Some of the bits of the ring are coming from Italy, some of the bits are coming from South Korea, and they've got to match within millimeters of each other, and they've got to be identical. And so that sort of collaboration is really challenging, and to be fair, I think they're actually doing a pretty good job at the moment to get it close to being there. But you could say that the companies and the private investment, which is what's happened in the last sort of 5 to 10 years, that's really pushed things forward because they're not encumbered by all those international agreements. They're literally doing it with private money, and they've got the latest technology at their fingertips. So if I look at the magnets that Tokamak Energy is another company which are building tokamaks. Yeah. They're going to use different magnet technology to ITER. ITER's using magnet technology, which, is very old and it needs to be helium cooled. And why would you do that in today's world? You wouldn't. So
tokamaks, that's what the thing's called, isn't it? These donut things, they're called a tokamak.
Yeah, it's a Russian word.
It's a very cool word, isn't it?
Yeah.
And what you're describing there, which is lots of countries coming together and complexity in getting international research done, and then private money coming in and moving things along. It's a bit like what happened in the space industry, isn't it? With international space agencies working together, and then suddenly private money came in the 2000s and 2010s, and now we have SpaceX and all the other good stuff.
Yeah.
I'm going to get shouted at by the Modo team for being a capitalist here, but there is something remarkable about that. Now there are some downsides, of course, which is the private companies own all the intellectual property, and it's for profit rather than for the common good. But it does move things along, doesn't it?
It does seem to move things along. I've seen a lot of movement in nuclear fusion, and it allows you to diversify as well. So I've only talked about the magnetic confinement, the big donuts, but there's lots of other fusion technology out there. We haven't even touched on inertial confinement.
Oh, let's do some of these then. So we've done the tokamak donut. What are the other ones?
So you may have heard about the big breakthrough, which was the first time that a fusion reaction actually got more energy out than it put in.
Yeah.
And that was firing 192 absolutely vast lasers at a tiny, tiny gold capsule. So it really is the sort of stuff of
we really are in James Bond
007 territory at
Dr.
this
Evil
point.
stuff.
Yes. And yeah.
So, whoa, 192 lasers. What do you mean a gold capsule? As in a nugget of gold, or
No, it's a hollow little capsule in which they have this tiny pellet of fuel, and the gold capsule, as the lasers come into it, it generates X-rays, and these X-rays bounce around this little gold capsule and implode the fuel, and from that implosion they get the pressure that they need to cause fusion.
wow? So no plasma.
No, different sort of technology entirely. So that's
How big is one of those?
Oh, that hall is huge. I mean, football fields sizes.
Wow.
If I've not been to that one, and one of my colleagues actually at Imperial is better to talk about that, Jerry. But he's seen it, and he says it's absolutely vast.
Lasers blow my wife did she did a chemistry degree, and she did a lot of time in physical chemistry doing laser stuff. Massive things, and you have to be so accurate with them. You can spend weeks setting up a laser for one tiny little thing.
Yeah, they've been trying to repeat that experiment where they got a Q value, which means the energy out was 1.5 times the energy they put in. Of course, that's slightly false in that the lasers themselves then took, to create the sort of 2 megajoules of laser energy, they actually took 300 megajoules from the grid into the lasers. So the lasers are not efficient. So that's not probably the way that...
Yeah, it depends where you measure it, doesn't it, I guess?
Yeah. But then, as I said, there's loads of startup companies that are using different ways. So there's ones where they're firing projectiles. So there's a company that's firing projectiles at things to create the...
Physical projectile, like rounds.
Yeah, so they're very, very, very high velocities to create the sort of pressure. There's another company which has a kind of a mixture of the two, of magnets and confinement. So they have a big spherical kind of vacuum vessel in which they're going to spin liquid lithium. So it really is the stuff of kind of sci-fi here. And then they have these huge pistons which are going to squash it and compress the fuel.
So what you're looking for is pressure, right? So you can
Pressure
either
and temperature.
PV equals nRT, right? So you can either put the temperature up, or you can squeeze it.
Yeah. So there's lots of different methods to do that, and I would say that the private investment has allowed that to really sort of diversify and explore all sort of weird and wacky sort of ways of doing it. And who knows which one will come up trumps.
So how come all the money's going into the tokamaks then? Or is it not?
It's not.
Okay.
So I mean, Helion has raised a lot of capital.
And that's not a donut.
That's not a donut. That's a dumbbell shaped vessel. It does have magnets in that one, but again, it's a different technology. They're actually firing two kind of bits of plasma at each other and colliding in the middle.
Oh, we need to get some of these Helion guys on the podcast. They sound great.
Yeah, no, it's really interesting stuff. And their way of getting energy out is different as well, in that they don't go for the classic kind of heat up some water sort of route, because they have these magnets around it. When the two projectiles of their sort of plasma collide, it expands, and that energy itself pushes back on the magnetic fields and generates electricity directly. So they say that makes it more efficient.
So we've still got quite a lot of work to do in fusion. How much money is coming into this sector?
It's
put you on the spot there. Sorry.
Yeah, I mean, if you look at the sort of investment in some of these companies, it's in the hundreds of millions. It's maybe, I mean, ITER and that would take in billions from international projects, but it's in the scheme of things, for the reward that's there, it's not a lot of money, to be honest.
And what about the other side of the world? So is China investing in tokamaks and fusion?
Yeah.
Obviously they're big on fission plants. What's their view?
I'm not an expert on China's view, but they are pursuing fusion in their own right. So they have their own reactor, as do the South Koreans. So there's lots of other people looking at it, as the UK is. So the UK has its own program called STEP, which I should mention.
Yeah, go for it.
Otherwise, some
STEP?
of my colleagues may get very upset with me at UKAEA. So STEP is the spherical tokamak for energy production.
Okay.
So it's
not a donut now.
It's now an apple-shaped
Okay, an apple
reactor.
shape.
It's
Okay.
still magnetic confinement, but the core is squashed in. And again, that's something that people say makes it more efficient, and you can do that with the better magnets that we have available today.
I say, why bother with a donut when you could just do it in a sphere in the first place and then kind of levitate it all into the middle?
Well, I mean, it is something to do with the way that you control the plasma and the shape of the plasma. So there are specific geometries that work, but in the spherical tokamak, if you squeeze it in, you can make a much smaller reactor, which then has great efficiency from the point of view. Like ITER, as I said, is absolutely vast, whereas the spherical tokamak will be a much smaller reactor, which makes it economically more viable.
So I was going to ask you, what do you want to plug? Like, what's going on in the world of fusion that we should all check out, and how do we get involved?
I think there's lots of engineering there, so and skills, to be honest. The one thing that the nuclear industry really faces a crisis on right now is skills, and that's what I do. So, I run one of these centres for doctoral training. So if there's any young people out there who are looking for something exciting to do post their degree or even for their degree, there's loads of opportunities in both fission and fusion energies right now. And that's true for people who might want to change career. If you're in the fossil fuels area, a lot of your skills would be useful in the nuclear areas. So there's just huge increases in the amount of manpower at all sort of skill levels that's needed. So that's kind of one.
What does that mean in practice? So can people go on a website somewhere and look at, is it funded projects or funded courses? What does that mean?
Well, so for what I do at the doctoral training level, so the PhD level, then that is funded. That's funded by the UK government and by the industry. So it's sort of half and half funded. And there's two big centres for doctoral training in the UK. There's the one that I lead out of Imperial, but it's 5 universities. It's Cambridge, Bristol, Bangor and Open University. And then there's the northern one, which is run out of Manchester and has many of the northern universities involved.
Just quick shout out to Manchester there, of course. It seems to have, there's loads of nuclear folks working in Manchester.
There are loads of nuclear folks working in Manchester. Yeah, they are one of the big centres for nuclear energy. So there's that, but then there are master's courses around the country. Those tend to not be funded, so you have to kind of stump up your own money for those, unfortunately. But, in my view, they should be funded because they would be doing good things for the UK PLC if they were. So that's really all I've got to plug because I don't have a book or anything like that. I wish I did, but I don't.
When's the book coming out? And are you on Twitter, socials? Can we find you somewhere on there?
I'm not very good on socials, I have to admit, but I will put stuff onto the Imperial social media stuff. So we have various centres there. So we have the Energy Futures Lab, we have the Grantham Institute. I have my own departments one and various other ones.
Okay,
so
cool.
we will go through that. But yeah, I'm somewhat averse to social media myself, I have to admit.
And there's a couple more questions I've got for you. One of them is, what's your contrarian view? So what do you believe about the world that perhaps not everybody, or not perhaps, definitely not everybody else believes? And this can be about fusion or fission or all of the above.
So, I mean, I have various views on things. One is I'm always asked about nuclear fission and is it safe? And is that, and it's not really a contrarian view. It's just the view of I'd like to think of myself as an expert, having worked in the field for as long as I have. And that really is that it is safe. I mean, I constantly get asked about the troubles in Ukraine and whether that's going to cause problems. And it's really not. And that could be considered a controversial view. But I've said it to lots of people in the media. There's a thing about nuclear power. I'm talking about fission now, not fusion, which is that the more people understand it and get to know it, the safer they think it is. And then there's a thing that Michael Liebrecht says about hydrogen, which is the more people get to know about hydrogen, the less safe they think it is. Yeah. Yeah, I think that's true. And I think actually, although I said I'm not on social media, the only thing that's tempting me to possibly be on there is that I have seen the work of some influencers in the nuclear space, and they have done a really great job at putting out the message around what nuclear fission is actually about, and that, you know, it's going to save the planet, not harm the planet. And I think that's probably a controversial message in itself.
It's a shame on that, though, by the way, because you can't, these things, the security is so tight. Like a power station, you know, a gas power station, we could go and record a load of content there and do a walk around and have an interview and just kind of turn up with some cameras and do an educational series. With nuclear, it's just another game, isn't it? You have to lock your phone away, and it's just so hard to even wrap your head around it.
Yeah, no, I mean, they have everything there. So they'll, you know, it's guarded 24/7 and there's fences and yeah, so there's no one going to get in there. And even the reactor itself is heavily protected once you are inside. So it's, you know, they're very safe things. I mean, there's a reason why the Russians have set up like military points around the Zaporizhzhia thing, and that's because it's such a well protected place. It's an easy place to defend as a result, sadly. But yeah, so that's fission is a very sort of, people worry about it, but they really shouldn't, is my message. It's, you know, there's take it from an expert, there's nothing that's going to cause those plants any problems. On a nuclear fusion point of view, if you were being controversial, I think that comes down to the dates and when will it be available. I think we've already said that, but my view is that, as I said, it's a bit like a builder giving you a quote. Is it going to be ready in the 2030s or 2040s? I'm skeptical, because I think they will come across problems. And I know there's those challenges that we talked about, like the breeding of tritium. It's going to take us a few years to work that out. And when you come across those problems and challenges, it's going to take a bit more time. It'll be worth it in the end, but I just don't think it's not going to go towards net zero, in my view.
Okay, so it's an after net zero solution rather than a pre-net zero. That doesn't make it a bad thing, just to reiterate. But we just need to change the language around some of it, right?
Yeah. But that would be controversial, and I may upset some of my colleagues in Fusion by saying that.
Well, if you're listening to this and you're upset by this, please do write in. We'll post some stuff. Okay, I want to say a massive thank you for coming on the show and for joining us. We managed to cover fusion, fission, whether nuclear is safe or not. We could probably have you back on the show to talk about fission another time. There's loads we could talk about there. But until next time, thank you. And if you're listening to this, of course, please do hit like, subscribe, and all the good stuff.